Okay, last time we saw three different type of position vectors depending on which thing is constant, and depending on what thing is constant is how long or complex the velocity and acceleration vectors result. Okay, today we are going to try to apply whichever type of vector it is. We are going to try to apply it to the mechanisms we have been covering in the class. For example, let's start with the acceleration analysis of a 4-bar linkage. If we remember, that guy looks like this. Okay.
Teacher, is it the same, a 4-bar linkage, a 4-bar, what was a 4-bar chain, and is it the same when they refer to, like
Yes,
in
yes, they
this?
are. Yeah. A linkage is a combination of links. That's why I use the word linkage.
Okay.
And if you remember, the vector loop proposed to solve the position was this one. Right? That is not new. That has been mentioned in two topics now. Um, and can you remember the labels we use? I think this is R1, this is R4, R2, and R3, so that the position vector loop equation end up being that one, right? Well, let me correct this. Got it? And then we work out the velocity vector loop equation. Well, before writing the velocity vector loop equation, which were the outcomes in this in the position one? It was theta 3 and theta 4, both as a function of theta 2. What about the velocity vector loop? You remember which was the vector loop? Which one disappears and how I end up, which is the equation I end up having?
Um, we eliminate R1.
So we end up having only that. And it's not that we eliminate it, it's just that it is constant and it doesn't appear when we derive it with respect to time, okay? Which were the outcomes of the velocity vector loop equation? Anyone?
Omega 2, omega 3 and omega 4.
As a function of omega 2 and whatever was taken in the position and analysis. Okay. Now the acceleration analysis consists of deriving that one with respect to time. When you derive that with respect to time, you end up having acceleration vectors. All of these vectors, these ones here, they have something that changes with respect to time. So none of them are going to disappear from the acceleration vector loop equation. This bit here is called, well, I'll put it on top, the acceleration vector loop equation. Okay, everything that I put with this color is the past. This color is new, or roughly new, because we started the topic last time. Okay, Now, in case you don't remember or you tend to get confused, always do the table. Check which type of vectors we are looking at. Identifying which nature we have for the magnitude and the orientation. For example, for vector R1, what happens with the magnitude and the orientation?
Is constant and constant.
That's why it disappears in velocity. What about R2, R3, and R4?
Constant variable.
and variable.
So these are links, right? And links, they don't change their length. And when they don't change the length, the magnitude stays the same. So magnitude stays the same, but they are allowed to rotate. So orientation is changing. And can you remember from last session notes what happens when I have this nature of vector? So if my vector is a CV, the position vector was cosine. I'm going to put the general one here without subindex. Any of you remind me what the velocity vector is equal to and the acceleration vector is equal to?
The velocity is r omega times minus sine of I plus cosine of j.
Okay, that was Majo.
Yes.
Okay, what about the acceleration? Another one. Let me ask Erika. Can you tell us which is the acceleration vector when the position vector has constant magnitude variable orientation, please?
Yes, it's r alpha times minus sine of theta I plus cosine theta in j plus r omega to the square times minus cosine of theta minus sine of theta.
Okay, all this was, thank you, Erika. All this was explained last class, so we don't need to, we don't need to go into the details. And if that is the acceleration vector, so acceleration, velocity, position, I need to substitute this type of vector in that equation for each of the vectors. Okay, so let's do that. It's going to be long, but let's take it easy. Okay, I'm going to simplify and I'm going to use the nomenclature that we have used before. For example, sine of theta 2 is going to be simplified as S2. Cosine of theta 2 is going to simplify as, oops, C2, and same for theta 3 and theta 4. So I start substituting then. I'll have R4, alpha 4, and then minus sine. I think you can do that on your own. You don't need to wait for me. And plus R4 omega 4 square minus cosine. Oops, not use cosine. Minus C2, C4, I plus minus sine 4j. Yeah, all that is just this bit here. ¿Sale? All that is just that bit. all that should be equal to the same thing with subindex 2. So I'll see if I can cheat. Copy this, put it here. Beautiful. Plus, and I'm going to change the subindex in a second. Whoops, a little bit low. Whoops, a little bit high. I'll get it right at some point. Kind of. Okay, change subindex. Oops, I might not be able to survive. Eraser is too big. So this is R2, omega 2, sine of theta 2. This one was cosine. Yeah, cosine of theta 2. R2, omega 2, cosine of theta 2, sine of theta 2. And all these have to be for R3. So, Jesus Christ. No me pude salir con la mía, sorry. Almost. That is the expanded version of the acceleration vector loop equation. It's very long. What we need to do now is identify what we know and we don't know. Then we, as we did before, we split this into vertical and horizontal components. So let's do that. Let's use this color for knowns, and I'll circle the unknowns. So let's go one by one. Check if I know it, if I don't know it. What about R4? Do I know it?
Yes.
I know all the R's, right? This is a 4-bar. Normally, the lengths of the links are given. So I know that guy, this guy, this guy, this guy, that guy, and that one. Do I know alpha 4?
No.
I don't know it. That's actually the thing I want to work out after this. So I don't know alpha 4. Do I know theta 4?
Yes.
I know it now because I have solved
Yes.
the position. Okay, so this comes from the position.
We're going to solve it in MATLAB, or we are going to solve it everything by hand, Prof?
Depends on how powerful you think you are.
Oh my God.
So this one, I'm going to write the solution for you. But for example, for the assignment one, the system of equation is not that complex. So I think you can survive solving it by hand, but you are free to use MATLAB if you want, up to you. Because I am not very strict when it comes to solving the system of equation, because I think that that is related to numeric methods or math. And I'm here to evaluate how good you are in analyzing a mechanism, not how good you are at doing math. If you're not good at doing math, then I don't know what to do with you, but that's someone else's responsibility. My job is to teach you how to analyze a mechanism. So analyze a mechanism means understanding where these vectors come from and where I can use it. That's mechanisms. How you solve the system of equations, you can even use a super powerful calculator, up to you. What about omega 4? Do I know it? Now I know it because I have solved the velocity. Alpha 2 is a special case. I'll leave this mark here and I'll come back to it later. Theta 2, you have control on it, that's the input, so you know it. Omega 2, that's also an input value, so you know it. Theta 3, I know theta 3, I have solved the position, so I know it. So that means I have solved also the velocity, so I know omega 3. What about alpha 3? That's also an unknown for this system. Okay, alpha 2 only exists if the input velocity is not constant, right? Keep in mind that alpha 2 comes from deriving omega 2 with respect to time. And in this case, let's assume that omega 2 is constant. So if I assume omega 2 is constant, all that is useless because alpha 2 is going to be equal to 0. And if alpha 2 is equal to 0, then all that bit disappears. So in your notes, you should add, assuming omega 2 is constant, okay? Let's split this into vertical and horizontal components, whatever happens at I and whatever happens at J. And if I do that, I'll have here R4, alpha 4 minus, yeah, this comes from this minus here. And I'll have minus R4 omega 4 cosine of theta 4 equal to R2 omega 2, oh, this is a square. This is minus cosine of theta 2 plus R3 alpha 3. This will be also minus, sorry, everything is minus here. Sine of theta 3. Do you realize I just, look what I did. This is my number 3. Jesus Christ, what's happening to me? Sorry, peeps, you deserve the best. Look at that fashion, number 3. Okay. That's it for, no, I'm missing the one with omega. So minus R3 omega 3 squared cosine of theta 3. That's whatever is happening horizontally. Now let's go vertically. And vertically I have R4 alpha 4 cosine of theta 4. Sorry, again, this is minus R4 omega 4 square sine of theta 4 equal to R3 alpha 3 cosine of theta 3 minus R3 omega 3 square sine. Okay, and you need to work out this, you need to solve the system of equations for alpha 4 and alpha 3. So using these two equations, solve for alpha 3 and alpha 4. Keep in mind this assumption here. That's important. And you don't need to worry. I have solved the system for you. I have the equations ready for you to calculate alpha 3 and alpha 4 when I have this condition, when I have this vector loop and I have this assumption. Here we need to add something to this because this is now for acceleration. So you could add, if you want, that you'll have some changes in angular velocity of this one. So you have alpha 3 and in this one alpha 4. Here you will have only omega 2. Okay. Let me write down the system of, the solution for the system of equation. I have it here in a piece of paper, so I'll copy it. You can have it in your notes. Also, it is in Canvas already in a presentation. In case you are falling asleep, you can carry on sleeping and you can check Canvas later. Right, Pablo Candelas? I'm not saying you are sleeping. I'm just consulting you as a colleague today. Como colega, nomás estoy preguntando tú qué opinas. Que se duerman, ¿no? Y que chequen Canvas después. So alpha 3 is equal to a big thing. Don't get scared. Here I'll have R2 omega 2 square, parentheses, cosine 2, cosine 4, plus sine 2, sine 4, parentheses, plus R3 omega 3 square. Omegas are always square in acceleration. Cosine 3, cosine 4, plus sine 3, sine 4, minus R4 omega 4 square. Divided
Profe.
by, yep.
Una duda. ¿Por qué en la ecuación de para J no se puso el R2W2 para el seno?
Which one?
Para la de las J.
Es que estabas asumiendo que es 0, porque la velocidad es constante.
No, creo que ahí se le fue.
Which one I missed?
You
Oh,
missed
I missed
R2
R2 omega. Yeah,
omega 2.
R2
Ah, sí, cierto.
omega 2 minus, yeah, you're right, minus sine of theta 2. This is squared. Yeah, sorry for that. Thank you, Paul, right?
Profe,
Yeah.
but we have to write them even though the angular velocity 2 is going to be constant and it's going to be 0.
No, what this here is the alpha 2, not omega 2.
Okay.
Omega 2 has to have a value, otherwise it doesn't move.
Uh-huh.
Okay. I'm going to copy this bit so I don't need to write it again. And I'm going to add now the subindex. I should have thought about this procedure before. Write everything without subindex. Bad. Now for alpha 4. Oh, it's actually the same. I could have done it with subindex. I feel not very intelligent today. Sometimes it happens. Sorry, Esme, for not being perfect today. It happens, you know. Probably it's because I'm thinking already about the weekend. I don't know, which I'm not going to do anything special. So I don't know why am I thinking. I'll stop cheating and write the whole thing because I realize it doesn't work for me today. Just don't add that to the ECOAS. No sabe copiar y pegar. 0. Those are the two equations. Pips finally got them right. To calculate angular acceleration of link 3 and angular acceleration of link 4, once you have solved velocity, position, and you are assuming that the input velocity is constant. Okay? So let me show you some cool stuff. As always, there's something cool after the equations. This is the code I've been showing you for a couple of weeks already. So I have lengths of the links. This is also created to trace the path in a triangular link. But right now I'm not doing that. I just want to calculate the accelerations. I have the input angle and I have the input velocity. Okay. Then in the for loop, I have, remember this, I showed you this last week, I think. This is for velocity, omega 3 and omega 4. Look at these two new babies here. These two new babies are very long, of course, long babies. These aliens are alpha 3 and alpha 4. What do I need to calculate alpha 3 and alpha 4? Well, I need the length of the links. These are the R's. They are there. I need the omega as input, omega 2. I need the angle, input angle. I need the calculated angle, theta 4. And I have theta 3 somewhere else, theta 3. I have the calculated omegas also. All I did, be patient because it is very long and you need a lot of parentheses to set up this equation, but if you do it slowly, you should get it, okay? And I managed to plot, for example, the acceleration alpha 3 as a function of the input angle. There you go, that's how it looks. And I also play with this guy here. This is also a guy that you know already. The 4-bar linkage or 4-bar mechanism or 4-bar, whatever you want to call it. And this thing is already alive, you know, it moves, whatever, yeah, happy, happy, happy. And I added the angular acceleration. There you go. That's the angular acceleration of link 3 in degrees per second squared. Okay, you know how to do this. Right click, export CSV, you get an Excel file, you copy that Excel file to, I think I have the Excel file here so I can show you. This is the Excel file you get when you export it. This is the two vectors you get, seconds and magnitude of acceleration, or it could be with respect to an axis. Ignore this, you don't need to, this is something else. So you have this vector, you can copy that information and you put it in MATLAB. This A3S means alpha 3 from SolidWorks. S means from SolidWorks in my mind. You can add SolidWorks, you can add whatever variable you want. So here I have it already. I have copied from the other Excel file and I pasted here. And then I included even this line here. You see, plot with respect to input angle A3S, which is alpha 3 from SolidWorks. So I plot this in the same graph. And look at that beauty. It's a total beauty because it matches, right? The dotted lines come from SolidWorks. The continuous line and a little bit thinner comes from the theory that we just derived a few seconds ago. You don't need to do this as you didn't do it for velocity. But if you do it and you show it to me, I know it's extra effort and extra effort demands extra points somehow. So if you do it, show it to me, okay? So that's about it in terms of angular acceleration for a 4-bar mechanism. Now we are going to, what time is it? I think we have time to analyze the slider crank. Okay.
Kike, can you go back to the notes? I forgot to write something.
I'm just going to go back to the notes in a second. Yes. Whenever time I resume recording, I feel that I'm back in live action. Me siento en un noticiero como regresamos del corte comercial. Bueno, ya que regresamos del corte comercial, let's analyze another mechanism, which is this other guy that you know, that you have worked with it before. Okay, so we are going to do the acceleration analysis of the slider crank. Which was the vector loop we used for this case? Anyone remembers? It was, sorry, that one, and the offset, right? Offset was R1, this one was R4, R3, and R2 and R3. Position vector loop equation was then just as above, which were the outcomes in this case. It was theta 3 and
R4.
R4 as a function of theta 2. Velocity was, what was the velocity vector loop equation for this one? I know these two appear equal to that one, right? Outcomes were omega 3 and linear velocity 4 as a function of theta 2, as a function of omega 2 and whatever was obtained there. So the acceleration of this thing would be, I derive that with respect to time. So I end up having these acceleration vectors. Let's do the table. I know I'm going a little bit faster than before because this is nothing different from what we did. The difference will come in a second. And I think you know which is going to be the difference. So magnitude, orientation, R1, R2, R3, and R4. R1 is constant, right? It's a fixed one. R2 is constant variable, R3 is constant variable. What about R4? Magnitude is changing, is the linear displacement of the slider, and the orientation is constant. For this type of position vectors, check above. So volteen para arriba, ¿no? O sea, están las notas ahí arriba. What about this one? What is...
aceitunas, profe, sus ojos.
Discúlpame por no ser tan perfectísimo. Bueno, usen unas aceitunas y voltean para arriba después, ¿sale? Position vector. Again, I'm going to do it general case. Yeah. General case means no subindex. And we obtain same orientation, right? Because orientation is constant. And we obtain linear acceleration this time. Okay, so position, velocity, and acceleration vectors. We saw this last time, just check your notes. Let's substitute them because this type of vector, you're going to use it in that one, okay? I'm going to remove the arrow because it takes a space, but just keep in mind that acceleration vector for link 4 it has this nature. Okay, let's substitute everything then. I'll see if I can copy and paste this time, wish me luck. So, which is the acceleration vector for this type, which is constant variable? It has R, omega, minus sine, sorry, minus cosine minus sine plus r alpha. I'm not adding this subindex now because I'm going to copy it, okay? So relax, don't panic. Minus sine plus cosine. Okay. And I have another one like that, so I'll add plus here. I'm going to copy this one. I don't have a space here, so I'll put it below. Oh, that's too below. You see, I cannot copy. Today is not my day. Sorry. Jesus, guy. Okay, I ignore that I'm crying. I'll add this to the index now. Jesus Christ.
Prof, ya ve, dice que el flojo trabaja doble.
That's very right. And I think it was Fabiola, right? Fabiola is always against me.
No, I'm not against you. I'm just being realistic.
This is also 2, subindex 2. All this corresponds to link 2, okay? Now goes for link 3. But you are very right, Fabiola. Let's not do that again. I didn't learn my lesson today. And the worst thing is that it's going to be recorded. I'm going to be very famous in YouTube because of this. I think this session today is not going to YouTube. It's going to Drive folder. Which I know you can upload it to YouTube and make many funny things, but let's assume you are not doing that. Okay, so this bit is because of that. All that is this. And finally, equal to linear acceleration 4 and the same orientation as in the position and velocity. Okay, and that's it. Now in this case, I can simplify this vector further because I know that it only moves horizontally. So I know the vertical component can go. So I can simplify this further. And I'm also assuming that the input velocity is constant. So this guy here, alpha 2 is equal to 0 because again, omega 2 is constant. Keeping that in mind, let's simplify and see what we get. I'm going to simplify and already split this into vertical and horizontal components so I can save some time. So what happens horizontally is minus R2 omega 2 squared cosine 2 minus R3 omega 3 squared cosine 3 minus R3 alpha 3 sine 3 equal to A4. And vertically minus R2 omega 2 square sine minus R3 omega 3 square sine plus equal to 0. Okay, from that, I know that the unknowns in this case, so again, let's use this nomenclature. This is known and this is unknown. I know the magnitudes. I know omega because I control it, it's input. I know omega 3 because it comes from velocity problem. I have solved position. I have solved position. This I don't know. This I don't know. I know all this. I don't know that one, and I know that one. Okay, I don't know alpha 3, which is the angular acceleration of link 3. So I complete this diagram now. I have alpha 3 there, and I have here a linear acceleration. Okay. Which I think it should be added, not like that, sorry. But here. Okay, now I solve the system of equation 4. So you need to solve that. Solve for alpha 3 and linear acceleration A4. From the second equation, the only unknown is alpha 3. So you can work out alpha 3 from there, and alpha 3 will be equal to, check if I make a mistake, please, because you know today is not my day, so it might be full of mistakes. Sorry, Cesar, because you have to suffer more mistakes at 11:30 later today.
Aren't they negative?
I don't think they are, because these two go to the other side positive, right?
Oh, sorry, I got the R3 negative in mind. I'm sorry.
No problem. Then you can substitute this. So you can substitute it there and solve for A4, which results as...
But teacher.
Yep.
A4 should have a cosine of angle 4 multiplying it, right?
But it's 0, so it's
in this case it's 0.
Okay.
Is equal to 0. Oh, yeah.
Yeah. Thank you.
There you go. Okay, peeps. 3 examples of mechanisms. Don't know where they come from, but you have them there. Tell me in which option, A, B, or C, you expect to have Coriolis component and why. Let me ask, who could be? Miguel Angel Perez. Tell me one option in which you expect to have Coriolis component and why.
I think in one that has magnitude and position and orientation variable.
Yeah, so in which case do I have that? Because that's the definition, Miguel. That's just the definition. But I see here in the chat that Maritza wants to participate. Están padricísimos. I don't know what she's talking about. I guess the mechanism.
I think in C. Maybe.
In C, maybe. Okay, let's see if I can have another opinion, and if not.
No, in A.
In A. Why in A?
Because link 1 can change its magnitude and also its orientation, right?
So link 1. Oh, why is so thick? Let me fix this before it moves. Oh, it is already fixed. Fix, okay. Link 1 will demand a vector that will go from this point to this point, probably. This is a slider. This slider is allowed to move along the link, and the link has a joint here. So that joint here will allow link 1 to rotate, and the slider can go in and out, or can move along the link. So this means that this vector here will be variable, and that means Coriolis. Sherlock is awake. Okay, what other option can I ask Pablo Ortegon? Pablo, can you tell me in which other option I have Coriolis component and why?
It would be in option B.
Why?
Because because of the same reasons, he can change his vector 1 can change his magnitude and orientation.
Okay. This vector here is allowed to rotate. It's not restricted to stay at the same orientation, right? And you have a slider. So this vector, at some point when this thing gets in, it will be shorter. So the magnitude is changing, but it has a rotation joint there. So that means the slider could be like that. So the slider is allowed to rotate. What is fixed is link 3, but not the slider. The slider is allowed to rotate. And because it changed orientation and magnitude, again, you have that, which means Coriolis. Now, last option, C. What do you think? Who do we have here? Anyone wants to volunteer, or should I pick one of you?
I prefer me.
Sobres. Salvador, do we have or not Coriolis component?
In that one, we don't have profe.
We don't have profe. Why?
We don't have because the slider will only move through the link 1, but the link 1 is not going to change
orientation.
Orientation.
So this is only going in and out.
Yeah.
But because
like the one we did in the lab.
This is restricted to keep the orientation the same. Then we have here variable magnitude, constant direction, and that is, sorry, no Coriolis. Okay, good. Let me show you another example. Show you another example. Okay, that's the other example. Do you think you'll have Coriolis component or not? Aaron, Saul, Cesar?
The link of D and E.
Yeah, the DC link.
Okay, can any of you draw the vector that is going to have both changing magnitude and orientation? Add the note, draw it on your screen, please. You can add the Gustavo's approach by doing super straight arrows.
But it's only the slider, yeah.
And that was Pablo Daniel, right? Okay, yeah. You see there is a joint at point C. That joint at point C is going to make that, is going to allow that link to rotate. And there is you're going to have to propose a vector to locate how far the slider is from point C. And that vector will change its magnitude because the slider is allowed to move. This is a more realistic way of representing oops, that. This is how you draw the diagram. But this is an slider. It's allowed to move along the link, which the link is allowed to rotate, which is exactly the same that we have on the diagram. Okay, just another example. Last example. There you go. Anyone else that hasn't been with us today? Julio, you are with us?
Yes, Professor, but I'm in the street right now.
You are with us
I'm
in the
in my car.
street.
Yeah, but tell me.
No, nothing. Carry on in your street. Let me ask someone else. Maritza, Coriolis or not Coriolis component in this one?
Yes.
Yes. You see, simple as that. No explanation, no nothing. See. Simon, you should have said Simon. Now explain us why, because we are not that intelligent. We need to know why.
Because in the...
Bueno,
Voy a dibujar.
ahorita se va a dejar de reír y nos explicará. Tengan paciencia.
A ver, ¿dónde dibujo? Aquí dibujo. In this component.
Okay, so that component, because again, you have a slider attached to a link, and the link is allowed to rotate. And the slider will give you variable magnitude. Okay, thank you, Maritza.
Nada.